Yes, so recording has started. Okay, good morning once again to all of you. So in last class, we are discussing about this CMOS inverter, right? And we have discussed, just to recap, that how to find the threshold voltage, or not threshold voltage, sorry. It is a switching threshold or a logic threshold for this CMOS inverter, right? And that is basically you have to equate the current because the same current is flowing through the PMOS and NMOS, right? And you know that this switching threshold will be in the region, that is in the region 3, where both the transistor PMOS and NMOS will be in saturation. From where you will get this VT, or logic threshold or switching threshold, right? These expressions. And from here we have also seen that if this logic threshold has to be near about in the mid position means it is close to this half of VDD, right? Then, we have to have these two conditions satisfied, right? The first thing is that threshold voltage of the NMOS and PMOS, the magnitude of both has to be same, and Kp should be equal to Km, right? For this case, these two criteria, when these two criteria is satisfied, then we will get this Vt will be nearly equal to this VDD by 2, right? And if we consider particularly for this case where this Kn equal to Kp, right? So where this Kn and Kp are what? These are the transistor parameter, right? For the process parameters, right? For NMOS and PMOS respectively, Kn and Kp. Right. And if we just substitute the write the complete expression of this Kp and Kn, then and Cox is same. From here you can easily get an estimation of what should be the ratio of W by L for W by L for NMOS and PMOS, because we know the ratio of mu p and mu n, or we know the ratio of the mobility. So as we know the ratio of mobility, we should be able to this criteria. From here, we have seen that the PMOS width has to be at least 2 to 3 times that of this NMOS, right? Okay.
Hello, sir.
Then we, huh?
Here COX should be epsilon oxide by thickness of oxide, right, sir? We should
Uh,
write it same.
correct. Yes. Oh, please do it correct. I don't know why I have done this mistake. Yeah, this is a mistake. So epsilon number C ox equal to, it is epsilon ox by T ox. Area is already been divided here. So it is the COX unit is farad per centimeter square. So the COX is the gate capacitance per unit area. Okay. So please do correct here. Okay. This yesterday I have written. So I thank you for correcting this, but you should have corrected in the last class itself. Right. So
Sir,
from here we have, huh.
sir, you had asked about CMOS amplifier.
Mhm.
So I think only it can be done if we fix the quotient point in the region where the slope is high, the gain is high.
That yeah. So we'll come to that. Okay, we'll come to that, but probably not discuss it much here. But I will put one additional class, means doubt clearing class. Maybe we can discuss this thing there. Okay, because this is not that way related to this particular course. Okay, but that would be interesting, to discuss that and to know your opinion on that.
Okay, sir.
Okay. Right. Yeah. Very good. That you reminded me. Yeah. So this effect of Kp and Kn, we have also seen that if this is the VTC for Kp equal to Kn, for Kp Kn, or this Kp by Kn, or Kn by Kp equal to, or better to write it as Kn by Kp, because everywhere we are writing it as Kn by Kp. So it is Kn by Kp equal to 1, right? For this case, if this is the VTC, then if we increase it, then we have seen the VTC should shift like this towards left, right? And for this criteria, that is when this Kn by Kp is less than 1, VTC should shift in the left ways, right? So that way we can control the switching threshold, right? And that also we have explained from these characteristics, right? The basic graphical way how to get this VTC, right? So to get some physical understanding why this is actually happening, right? Then we have also briefly discussed about the noise margin in CMOS. Here we have just discussed the procedure because it is type of repetitive. If you compare it with the other inverters that we have discussed earlier, it is almost the repetitive, but you have to just solve these equations a couple of times and find this VIL, VOH, VOL, VIH. And if you know these four parameters, you should be able to find noise margin high and noise margin low. In fact, I requested you to please complete it in your home. So I hope you have done that. And if yes, very good. If no, then today, no, don't worry. I will give you one homework today so you can again do it. So here, so few more points regarding the CMOS. Here we have discussed about this is VTC, and from if this is the VTC, then how does the drain current versus V in characteristics should look like, right? We have seen that the characteristics would be like this. Till this point, there will be no current because here this NMOS would be off, right? Here this NMOS is off, and here there will be no current because here PMOS is off, right? And to have the current, any current ID, both NMOS and PMOS has to be on. And that is only possible from this point, this side, and from this side, like between these 2 points, right? Right. And we have also seen there are from here to here, right? What should be the characteristics? Because one transistor will be in saturation, another one would be in the saturation, and there would be the triode region. And from region A to B, right? This would be here, both the transistor would be in saturation, and the current would be maximum at this VT point only. Expected drain current characteristics would be somewhat like this. And we have also discussed why the nature would be like this, non-linear, right? This curvature nature. Because here it is the relationship is VG, basically V in square, right? That's why the shape should be like this. Now we have discussed about like the gain. As you can clearly see here, the gain, this is flat, so gain is 0, no gain. Here there is some gain, and here the gain increases significantly, and you will get maximum gain again at this VT point. So that is also clear from here. Then again the gain will fall down and gradually, and gain we can become 0 from this point onwards, right? So here there is a question your friend just reminded me that can this CMOS inverter be used as an amplifier? Means for some analog amplifier. Suppose you want to design an analog amplifier using this. So is it possible? So please think about this answer. And or you can also do try to find it using to take the help of this internet. And maybe on some other day we will discuss this. And I would like to first know what is your opinion on that. Okay. Now, if I hope, okay, any question so far? Okay, so if there is no question, then let us start today's class with which is lecture number 8 and 9 because now today we have a 2 hours class. So let us start our class today with an homework, okay, which is based on this CMOS inverter only, and you have to find the noise margins. Okay, so you can see here. It says like this, that a CMOS inverter is designed with equal size NMOS and PMOS transistor, where the widths are same, right? Equal size. So the widths are given as W and meter in a 0.8 micrometer CMOS technology. So this is basically one technology node. So you can consider as of now that this is close to that gate length. Okay. And given that gain dash value, KP dash value, and threshold voltage of both these transistors are also given. VDD is mentioned as 3 volt. Okay. LN and LP, right? That is the gate length. That is informations are given to you, and you need to find this VIL and VIH, and basically you to find noise margin you need like these two as well, right? So no need to explicitly mention this, right? So please do this, and please do this by tonight. I will share the solution for this problem tomorrow, okay, in the group email. Okay, do you have any question for this homework? Okay, so if no, then very good. So this is the last part that we have discussed very briefly, maybe within a 1 or 2 minutes yesterday, right before we end. So we need to start from here. So scaling of the supply voltage in a CMOS inverter. So in a CMOS inverter, suppose this VDD, okay, for in a particular technology node, it is 2.5 volt, right? And the threshold voltage of this PMOS and NMOS magnitudes are equal and they are equal to 0.5 volt magnitude. Okay, and obviously I am not saying every time that the threshold voltage of PMOS would be negative, threshold voltage of NMOS would be positive. That you should know by this time, right? Okay, so the VTC for this case would look something like this, and say we have designed such that the VT would be nearly equal to half of this VTD. So we will get a VTC which is close to, which is almost like this, no? Right. Now, here is the question. So what will happen if we now keep on reduce this VDD? What will happen? Okay, so say with like as discussed yesterday, say we have make reduce it from 2.5 to 1.5, then 1 volt, then say 0.8 volt, even say 0.2 volt, which is, see, you can, this voltage is below the threshold voltage of both the transistors. So what do you think? Or will it not work? Please let me know. What is your view? Yeah, Devdotto Hayat, Dheeraj. Dheeraj, can you hear me? Okay, so can I then consider that the Dheeraj is absent in today's class? Okay, so Dheeraj. So, like Dheeraj, I'm considering that you are absent. Okay,
So is it me or
yes, it's you. So, why, where, like, are you present or like you're
yeah,
somewhere else?
I had to go out for some
So, what is your opinion on
about
this?
can you please ask
Sorry.
can you please ask the question again?
Okay, why I can do that, but the thing is that why you are asking me the same thing once I have asked you? Why you have not asked me
Uh,
before? Before I have asked you.
Actually, I just came back.
Okay, so the question is something like this. So here for this CMOS inverter, VDD is 2.5 volt. So what will happen if I reduce this VDD or the supply voltage? See, if you are reducing VDD, that means at the same time you are reducing V in as well, right? Because this VDD, the maximum voltage of V in will be equal to VDD, na? Right?
Yes.
So if you reduce this 2.5 volt to 1.5 volt, 1 volt, 0.8 volt, 0.2 volt, then what do you think? What is going to happen? Yes, Dheeraj. I hope you have understood my question,
Yes,
right?
sir. I understood your question.
Yeah. Then what is your opinion? Okay. What about Harsh Mohan? Harsh, what is your opinion? So Harsh is also absent. Okay, so Harsh is also absent. So I will put these names here for my reference. Okay, so Madhav Raju Nair, Nand Ram Prajapat, Nand Ram Prajapat, Vishwabashu Roy.
Yes, sir.
Yeah, could you please? Yeah, thank you for answering. And could you please let me know your opinion?
Sir, I think if we take it very low, like if it is less than 0.5 volt, then VGS will always be less than 0.5.
Right,
In that case, the transistors will always remain off.
right.
So
So in
that
that
low
case, you
voltage
think
won't work.
okay. So in that case, you think that inverter will not work, right?
Yes, sir. Otherwise, there will always be a
Right.
cutoff region and a triode or saturation. Otherwise, I think it should
Mhm.
work.
Okay, very good. But can you please also answer one more question regarding this? That is, like, why we should even bother about reducing this VDD? Is it means are we gaining something if we reduce this?
So, like in analogs, we were taught that it may be some kind of battery or something which is the supply and it can reduce with time.
So
Please
basically,
repeat it.
if we
Huh.
reduce this, we can have a brick wall kind of response in this VTC. Like, I mean, the region 3 will be exactly aligned.
Region 3 will be exactly like, okay. Anything else?
I mean, there is kind of perfect switching.
Mm-hmm. Okay. Okay. Anything? Okay.
And sir, below 0.5 volt, basically V out is floating, so we don't know what uh, voltage it would take.
Okay. 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 So let us not even consider 0.2 as of now. Okay. Let us consider up to 0.8. So then why should we bother? Like, why should we decrease this VDD?
The low power, very low power.
Low power, right? That is one of the vital point. Because see, we will see that the power consumed, okay, in this type of circuit is actually proportional to VDD squared, right? Power consumed is actually proportional to VDD square. We'll see it, right? So as you can see, the power is proportional to VDD square. So it makes sense to, if you can reduce this VDD, then the power, the required power, you can reduce significantly, right? So that is one of the driving motivation why we should try to reduce the VDD, right? One more thing is that as you scale down, as you scale down your device, that means suppose earlier this was the transistor, right? And this is the gate length, right? So here, so suppose this is source and you have grounded it, and here you have applied VDD. So this is the gate length, right? And so VDD is okay. Suppose VDD 2.5 volt is okay for this particular gate length. But if we now shrink it, okay, for better performance, and then obviously you see the gate length has reduced. So at the same time, there is no other way, but you have to reduce this VDD as well. Okay, because otherwise this material can even break down. Okay, so all these things also will come with the technology scaling part. But
Sir,
here, yeah,
sir, but reducing L is limited by technology, right? Because we cannot reduce it after a certain extent.
right, true, true. Reducing it reducing the gate length is actually there isn't some technology limitation beyond which we cannot do that. But whenever you are reducing it, suppose we are considering 180 nanometer technology, and then we are considering say 45 nanometer technology, then obviously you can see there is a significant reduction in the gate length, right? So if you consider these two technology node, then do not think that the VDD that you have used here and the VDD that you have used for this 45 nanometer technology are the same. Okay, the VDD used here, if we say like VDD2 and this is VDD1, then obviously VDD1 is higher than this VDD2. Okay, you have to also scale down this supply voltage because it makes sense. See, when you are reducing this gate length, at the same time you have to also reduce this C, you have to also reduce this T aux, right? And so when you are reducing this T aux, this oxide has a particular breakdown electric field. So when you are reducing the thickness, the maximum voltage that you can apply on top of this gate, that also reduces. So as a result, you need to reduce this VDD as well. Okay. Okay. So the thing is that, okay, so what is the scaling, why you should scale the, okay, first of all, let us discuss this part, that scaling of scaling of the supply voltage. What are the positive things, right? Positive, then it is of definitely a positive impact. Positive impact on power consumption. Right? But if this is the positive impact, okay, and then can you please mention that if I reduce it, if I reduce this VDD, then is there any negative impact of that as well?
So the level 1 and level 0, they would become very much close. So
so you are trying to say that the system become quite prone to the noise, right? External noise.
yes, sir. Yes, sir.
Okay, so it will be more sensitive to the external noise. Yeah, points taken. Anything else?
So also there may be less headroom for like gain and something.
Gain. Why there would be less? Means what do you mean by less headroom for gain? Means what?
Sir, the center point will be like very less, so the gain swing will be very less, I guess.
Yeah, swing. But how does that affect the inverter performance?
If you have to make an amplifier, then only.
Oh, they can make an amplifier. Okay, for inverter.
For inverter, I guess it will be fine.
It could be fine. Okay, okay. So one thing your friend that has mentioned that the system would be quite sensitive to noise, right? Let us say external noise, because obviously the noise margin will reduce, right? Definitely, if you reduce VDD, noise margin is also expected to reduce. Anything else? Can you think of something else? Okay, what about the current ID that will be flowing through this?
So that would decrease.
That would decrease, right? So VDD decreases, ID decreases. I hope this part is clear to you, because ID is proportional to the same saturation. It is VGS minus VTH square. VGS is nothing but VDD minus VTH square. So if this reduces, ID has to reduce. Now, what will be the implication of having less ID? Anyone? For this transistor action? For this inverter action? Please say it quickly. Okay. This inverter is driving what? What is connected at its output?
Capacitor.
Capacitor, right? So it is driving one capacitor, which is an say like maybe this inverter is driving another inverter, right? So you can think like this same thing is there after this, right? So the gate capacitances of these two is the load capacitance for this. So it is driving an external capacitor, right? Okay. Now can you comment if the value of ID reduces, this capacitor, the charging time for this capacitor will reduce or increase?
So increase.
It increases, right? Because less current, it is it is like, then it will take much more time for you to charge this capacitor. Is this clear to you?
Sir, but the RC thing would still remain constant.
Yeah, RC thing will remain constant, true. But what about, yeah, that is one aspect. But what about the current that it can
No,
flow?
sir, current is reducing, but at the same time, maximum voltage will also reduce.
Maximum voltage will also reduce. Yeah. So suppose this capacitor, okay, this capacitor you need to charge, say completely to a particular, say, okay, this, say this charge is type of a bucket, okay, and you need to fill this bucket. Now you are filling it with a pipe. Pipe is, and the flow of water through it is the current, right? So if you are reducing this current, so to fill this bucket, will it take less time or more time?
But the volume of bucket has also reduced, right?
Okay, why volume has bucket has reduced?
Because the maximum voltage it will reach will no longer be 2.5 volt.
Yeah, maximum voltage will no longer be 2.5 volts. So how much will be the there? So how much will be the reduction? So suppose if you are considering, say, 2.5 to, if you reduce to 1.25, right? Then how much will be the reduction
So it
in
will be
the
now
total?
1.25.
Okay, so how are you saying that the total volume of this bucket will also reduce? Could you please also explain that point?
No, sir. I mean the charging time depends on the final voltage as well as the current, right?
Final voltage as well as the current, right?
Yes,
But
sir.
the
So,
total, okay, so I am now considering in terms of charge. So can you comment on that in terms of charge? So what will happen? So suppose this capacitor can store this amount of charge. So can you comment that whether the amount of charge is decreasing, required charge is decreasing if you are reducing it from
yes, sir.
Sir, the
2.5 to
charge
Capacitance
is
1?
remains.
proportional to voltage.
Sorry?
Like, sir, Q is CV, right?
Huh.
So if V decreases, we also require half the charge. So it doesn't affect, like the charging time, sir. Time constant we take as RC. R and C are not changing here because C depends on the physical parameters of capacitor, and they are not changing. Therefore, the time constant should remain same.
Sir, RC is actually
So the R is changing and that
yes,
can be
it is
directly explained.
increasing.
Yeah,
It is
so we're looking into the drain side of basically the say the NMOS portion. So we
Mm-hmm.
know that the R will be roughly R naught. Like there's a huge expression, but proportional to R naught. When
Mm-hmm.
it's
ID
R naught
decreases,
by
the R
2.
naught will increases.
Are not increases. So you are saying that the resistance is also changing.
Yes, sir.
Yes.
Okay. Okay. So the resistance is also changing. So your friend was earlier saying that the resistance is remaining same. So is it then valid? The resistance, is the resistance remaining same?
No, sir. The resistance is basically R naught of the NMOS parallel to R naught of the PMOS,
So R
and
naught by 2.
R naught is proportional to 1 by lambda ID. So obviously R naught is inversely proportional to ID. So if ID decreases, R naught increases, RC time constant increases.
Yeah. So
And it can, I think it can be viewed in this way also, like ID is proportional to VDD square. But
right.
so if
ID is
VDD,
proportional, exactly. ID is proportional to VDD square.
if
And the
VDD is
decrease, what you were saying, is basically related to, this is related to proportional to square, and this one is related to VDD.
linear, yes. So that's why it will take more time.
Right. So is this clear now?
Yes, sir. Yes.
Okay. Okay. So then, so what is the then verdict? So if you reduce this VDD, what will happen to the charging time? So gate delay increases, right? So basically the gate delay increases, right? Okay. So we have understood, right? What is the positive impact of reducing this VDD and what are the negative impacts, right? So positive impacts, one of your friend also mentioned that the switching would be faster, that the switching we had not considering that way right at this moment, maybe in later portion when you are considering the propagation delay and all these things, we can take a note of that. But as of now, it is the positive impact on the power consumption that is very important. And in certain situation, on certain design criteria, the reduction of the power consumption would be the primary objective, right? So there, the reduction of VDD would be the major thing. Okay. So, but at the same time, we should also know when you are reducing this VDD, what is the negative impact. So these are the negative impacts, but we have to make find some common ground. Okay. So what should be the noise level which is acceptable to us, and what would be the gate delay which is acceptable to us, right? After and what are the power consumption level that is also accepted. It's basically type of a trade-off, right, between these two things. So if you want to achieve something on this side, obviously we are going to lose something on the other side, right? Okay, so now let us come back to the previous question. So what is going to happen if this VDD is reduced from 2.5 to 1.5? The answer is, if you enact 1.5, nothing will going to happen in terms of this VTC. VTC will be this inverter will expect it as it is, and you will get an VTC for 1.5, which is like this. If this is 2.5 and say this is 1.5 and this is say 1.5, so this is 1.5 volt. Say this is 1.5 volt and this is say 0.75 volt, then you will get VTC. After 0.5 it will be constant, then it will give a swing, right? And then after that again it will be something like this, right? Okay, what will happen for this around 1 volt? Okay, the around 1 volt also you are going to get one similar type of characteristics. Say this is 1 volt up to 0.5, and then there is a good amount of like almost quite close swing. Then okay, now here is the question. So 0.8 also I hope you will be able to explain. So now here is a question: will it work for 0.2 volt, whereas the threshold voltage of this each MOSFET is magnitude is 0.5 volt? The answer is yes. Even at 0.2 volt it will work, and you will get a VTC which is something like this. Now, now the question is how is it possible, right? How is it possible? That is, we are considering, yeah.
So, but then the VGS that is never less than VTH period, then how will it work?
Yeah. So here our assumption is like, if this VG is less than the threshold voltage of MOSFET, whether it is NMOS or PMOS, you can put it in that context, then the transistor is never on, right? The current is zero. But that is not the correct thing. We will see it today only, because even when the gate voltage is below the threshold voltage, this transistor does conduct. There is some current called the subthreshold current, which will be still flowing. And the subthreshold current would be sufficient to show this VTC characteristics for this inverter. Okay, eventually for gate voltage, V gate, as if it is more than 4 kT by Q. kT by Q, at room temperature it is 26 millivolt, right? Even if this gate voltage is greater than this, or not gate voltage, I should say VDD, that makes much more sense here, right? If this is VDD is greater than this would work. This inverter would work. Okay, because of this sub-threshold. This is because of this sub-threshold current. Now, what is the sub-threshold current and all these things? Maybe I think I have I put it in the next slide? Yeah, I have put it in the next slide. So that we will discuss in the next page only, right? So, so you can see then, right? If you can actually reduce even this supply voltage below the threshold voltage of this individual MOSFET, and eventually you will get an inverter action from this, right? It will work, right? Now,
Sir,
yeah.
sir, but as we discussed as a negative point, the charging time of capacitor would increase. So after all, we'll be using this in some kind of digital circuit, right? And if the clock cycle, like if it has more time constant, then we would require a slower clock and therefore reduce the whole performance of system. So is it fine for like this greater than 4 kT by Q? Do we get acceptable operating range for clock pulses or?
No, see, the thing is that suppose, okay, maybe one quick example that I can give you right now. Suppose if you are making some digital clock, okay, so for you make a digital clock, the frequency that you need, clock frequency would be very less, right? So for that,
Sir, for example, in the digital circuits or the actual systems of computers that are used, in that the frequency is quite high, right? It is in gigahertz range.
no, that's what, it would be like in those applications, it is not possible. But I'm saying this inverter would still show the VTC. It does not mean that, delay, this clock frequency, everything will be aligned accordingly. No. If somebody asks you like whether this inverter will work, the answer is yes, it will work, but you have some negative issues as well. These are the negative issues. Yes, Arsh, was this your question or you were asking
Yes,
something
sir,
else?
I get it. I get it.
Yeah. Right. So quickly, some of the things, before we go to the subthreshold slope, here I'll discuss subthreshold slope. So basically, this I have discussed as well earlier that whatever the equations were, analysis we have done so far, and we have used this type of equations, right, which is also, right. So these are basically valid for long channel MOSFET. So long channel MOSFET means this is the channel length when the channel length is sufficiently long. Now which particular gate length is long channel and which particular gate length is a short channel, that is a separate discussion. But long channel is when the gate length is significantly long. Now compared to what? Please try to find it out. What should be the reference? When you will say that this is long channel and when you will say this is the short channel. So there should be some reference. Na? So this is another question from my side. Please try to find what should be the reference, with what we should differentiate. Okay. So here the channel length is significantly long. So we are calling it as long channel MOSFET. And for this ID expression in linear region, this can be written in this way. And ID expression in the saturation region can be written in this way. So this is in the linear region and this is in the saturation region. Right? This, no issue in that. Now, we have also seen this type of plot, ID versus VDS, which looks something like this, right? Here, this VGS1, VGS2, we are changing this VGS and we are getting these different plots, right? And it looks something like this. So here it is VGS1, VGS2, VGS3. And here, the important thing is to note is that we are changing this VGS on a regular interval. That means the separation between these two is equal to the separation between these two is equal. Right? So that's equal spacing. So if it is 1 volt, say it is increase by 0.5, so 1 to 1.5, 1.5 to 2, 2 to 2.5, like that. Huh? So equal spacing between them. But have you noticed the spacing between them? See the spacing? This is the highest spacing. This spacing is getting bit reduced, right? Gradually, this spacing is becoming reduced. I should not put here the last one because my drawing is not that way perfect. So yeah, up to this portion, you can see there is a reduction in the spacing, right? So is it also expected from this equation?
Yes, sir. Square relation. So
It is a square relation, right? So as you are increasing this VGS, so the higher this VG, the more should be the spacing compared to the previous one. Right? So maybe in some previous drawing we have make equally spaced this the separation. So please do remember that that is not, but because it is our general tendency. So particularly when I am using this ruler line, so I will take it as a reference to draw the straight lines, and that way my lines will be almost equally spaced, right? But that is not the correct thing for the long channel MOSFET, particularly when we are writing this equation. Okay. Right? So please take a note of that. If you see this type of characteristics, then it is correct for long channel. If not, then that is not a long channel MOSFET. Okay. Now, probably we can also plot it in this way, right? Oh, this is not VDS. So probably we can plot one more thing here. I can plot ID versus VGS, right? Gate to source voltage, right? Because in this equation, I can plot from this way, ID is equal to 0 to VGS. And that, it would look something like this. Right? So here, this particular voltage, after which the current will start, we call it as the threshold voltage. Right? That this is the threshold voltage. And when you cross the threshold voltage for a particular, and particularly this, we are plotting for a particular VDS. So here VDS is fixed. For example, when you are plotting this output characteristics, you have fixed one VG and you are plotting the characteristics. Similarly, here you have fixed this VDS and you are varying this VGS, and see how ID is varying. So ID will look something like this. So when you get to this region, you see what is the equation. This particular equation, see, it is basically a square. So it will get an curved line, something like this, right? Okay. Now, one minute. Right. So you are expected to get a quadratic line here, right? Okay. And so whenever you are seeing that is a quadratic line, then you have understood that this particular transistor is being operated in the saturation region, right? If this transistor is operated in the linear region, then obviously you can see from here the characteristics would be little bit different, because here the ID is proportional with VGS, so it should be linear, right? If you see some region which is linear, then obviously it is in the linear region from this plot. If it is type of this quadratic nature, then obviously you should understand then the transistor is entered into the saturation region. Again, the entire thing will depend on this VDS and VGS value. So maybe for particular VDS, it maybe look like this. For if you change this VDS value, the nature of this curve will also change, right? Okay. Now here is an interesting thing. The thing is that this particular, when you are plotting this, but here as well as here, okay, both this linear and both this x-axis and y-axis are in linear scale, right? This is in linear scale.
Sir, the portion you referred to is quadratic. Shouldn't that be the linear region?
Should it be linear region? Please check it out. That here it is VGS, na?
Yes, so VGS is high here. So VGS minus VTH greater than VDS, something like that. So
Okay. What about, I have not mentioned the linear region here. So linear region might be after that.
yes, yes, that can be.
Right. Right. So that's what I mentioned, that again, it depends on this VDS. If you change this VDS, the nature of this curve will also change. Right. Okay. So here it is in linear scale, both the y-axis, right, as well as the x-axis, right? Now the question is, what will happen, okay, if you plot the same, right, ID versus VGS in log scale, okay, log scale. So here, this is only the log scale, not this one, okay, this is linear only, VGS is linear, only ID is in the log scale. So when you plot this ID in log scale, the same characteristics would look something like this. Right? Are you able to follow? Now here, this is the threshold voltage. This is the threshold voltage, as here you have seen. So you can see after threshold, the curve would look something like this in log scale. And if you consider the below threshold, where it looks like current is 0, but actually you can see here the current is actually falling exponentially. So it is exponentially vary with Vg by Kt. Okay. So you are changing this gate voltage and this region will vary exponentially, right? Now, also one more interesting thing is that that even when this Vg is equal to 0 volt, the current is not equal to 0. This is log scale, right? In log,
Why is there a minus sign in exponential?
yeah. Okay, because okay, I wanted to mean that it would decrease as you were right. It should not be minus. You are absolutely right. That time I wanted to mean that with this will decrease, but there I was considering that the Vg is in the negative direction. Yeah, but in either case, it should be plus only Vg by Kt, Kt by T, or Vg by Vt. Right? So as you were changing this one, so it will in this would be the exponentially it will change, and even at 0 volt, the current would not become equal to 0, because in log scale you cannot show 0, right? So then obviously this is not a 0. So you have to see the finite leakage current. Finite leakage current even at VGS equal to 0 volt, right? So even if VGS equal to 0 volt, you have some leakage. So that means the transistor, say we are considering this NMOS, we have given here V in equal to 0. So that way we know that this transistor should be off, but this transistor is off, this transistor is on, this is off. But it does not mean that it is completely off. There is some leakage current, okay, and that leakage current will flow through both this, means if this there is a leakage current, that leakage current has to flow through this as well, right? So then there is will be some power dissipation from VDD to ground. Right. So that way earlier we have mentioned there is no static power dissipation, but you remember always I put a one star on top of that. So that was the reason that is it really true that there is no static power dissipation in CMOS inverter? The answer is no. There is static power dissipation even in CMOS because of this leakage current. Right? Okay. Now there are a couple of things that also you should know. So this particular region is called the subthreshold region, and it has a particular slope, right? This slope is called the subthreshold slope. Okay, sub threshold. I am writing just in short. Okay, subthreshold slope, and it is or sometimes also written as SS, subthreshold slope. Right. Ideally, you know that from semiconductor physics. Ideally, SS, the minimum value. Okay, minimum value. Do you know how much minimum value of subthreshold slope? What is the minimum value of subthreshold slope? Oh, you do not know. It is 60 millivolt per decade. Okay, 60 millivolt. This number, remember, this number is very, very important. 60 millivolt per decade, right? So that means, what does this mean? That means that suppose you are changing from 0 to here 60 millivolt. Okay, 0 to 60 millivolt. Then current should increase by one order. So here, say the current is 10 to the power minus 11. Then if you change it to 60 millivolt, then the current would become 10 to the power minus 10. Current should increase by one order, okay, of magnitude. So this is the subthreshold slope, and this is the theoretical limitation that subthreshold slope cannot be below 60 millivolt. But what is desired is that to design or fabricate transistor whose subthreshold slope is as low as possible. The reason is because, so let me explain it from here, this space, from this space only. See, the subthreshold slope remains the same, right? If you can reduce the maybe this color would be better, yeah, or maybe this color would be better. Suppose if you can reduce the subthreshold slope further, then what will happen? This curve can be considered like this, right? So there, right? With reduced subthreshold slope, you see the leakage current has significantly reduced, right? So the static power dissipation due to this leakage current will be significantly reduced because of this reduction in the subthreshold slope. Right, you might be considering how much we are gaining. Anyway, these currents are like very small. Yeah, this is true, but you should also consider, like in a modern IC, what is the number of total transistors? The total number of transistors also compare, in the range of 10, more than 10 to the power 9 to 10 to the power 10, right? So in that case, so you multiply this current with that number of ICs, then you will see the total power that you are wasting. That is actually huge. Okay, maybe in the later lectures, I will show you some plot where it shows what is the power dissipation density, okay, in an IC and how it is changing. Okay, and where do we stand in terms of, suppose if you compare the power density, dissipation density in terms of like power per unit area, that means that density I'm saying, right? How are we comparing with an say a furnace, okay? And atomic power plant, okay, and even with sun, okay, and you will be surprised to see that, okay, that what is the total power, means power per unit area that and semiconductor IC does dissipate. So this plays a very, very important role, that how can you, and this is one of the fundamental challenge. Ideally, what you want your transistor to be on and off like this, right? Like this red line here. Like this portion is off. When you put it below threshold, tuck, off, right? And if you can do that, then all these issues would be solved, right? You keep the battery as it is. Suppose you charge your mobile, do not use it, okay, and keep as it. It should not dissipate any power, and it should last as long as your phone is alive, right? If you're not using it. But nowadays that is not happening. Na? You charge your mobile, you keep it, even if you're not using it, it will continuously drain the battery. Right. So I hope now the static power dissipation, this point is clear to you, and also the subthreshold part is bit more understandable to you, right? And if it is so, then let us move to the next part where we are going to differentiate between the long channel and short channel. So long channel MOSFET we have already discussed. These are the equations, and the characteristics would look like this. Here clearly you can see the separation is increased as you are increasing this VGS. However, when we do the technology scaling and you have reduced the gate length from here till suppose this, right? Then it makes a short channel. Again, what is the reference? That is a homework for you, right? And if you plot the current ID versus VGS characteristics for the short channel MOSFET, then you will get a characteristic something like this, where you can see the spacing between these lines would be equal, right? So if someone shows you one characteristics IDVD, this one, and one characteristics IDVD, and just by showing these two, you have to identify which one is showing the long channel and which one is the short channel, right? Then you should be able to tell from this the spacing, the gap between these two, right? Now, so this is the basic difference in ID VDS characteristics. Now, bit more detail. Okay, right. How to get this type, the equations? Okay, right. Equations, current voltage equations for the short channel MOSFET. So again, these are not very easy thing to do, because this is a part of this, equations. How to find this equation? This is a part of a separate course which is called semiconductor device modeling, and like circuit design engineer in different industry, there are device engineers as well, device engineers, device modeling engineers. So what is their role? Is that their role is that you give any new device, they will give the equation, mathematical equation for that particular device, that how this new device can be, or its characteristics can be represented by a mathematical equation. Many times it is physical. Physical means if like whatever the equations you are giving, it has some physical significance. And if you are changing, suppose changing the gate length from this little bit, say 180 nanometer to one, say the next step 150 nanometer, then that equation also holds for the next technology node. Okay, that is called the physical modeling. And if it does not, then it is called the empirical modeling. It's a basically type of just a fitting, but that is not preferred. What is preferred in industry is an type of more physical meaning, which has some physical thing. And if you, because that is also easier if you want to further incorporate some new addition on top of that model. Okay, so remember that in any one part is the fabrication part, one part is the circuit design part, one part is the device modeling part, right? And please try to differentiate between these three and their works, right? So here we will try simple things to find what are the equations, or how can we represent this short channel MOSFET ID/VD characteristics. Okay, from based on our previous understanding, and we will take a help from this previous long channel MOSFET equation, and we'll try to derive those equations from this only. And remember here, whatever we will derive here, that will not be physical. It is actually an empirical. Even not even empirical, it will be type of an first order analysis, simply for our hand calculation only. So please do not think that this is the equation which is going to, if you do, and you will get the similar result as you are getting from the say an standard circuit simulator. No, it is not, because this equation which we are going to derive is a type of very primary equations, and it's a level of first order. Okay, so a lot of things can be done on top of that, but that will make the equation much more bigger, much more complex, and difficult to handle. Right. So to know that, or to find those equations, one important thing is that whenever you are reducing the channel length, an important thing will come into the play, into the peak, means come into play, would be this short channel effect. Now, what do you mean by this short channel effect? See, as you are scaling this gate length, right? This is the gate length. Then what is happening? The separation between these two is source and drain is decreasing, right? Then if you consider what is the electric field E between these two, say this is ground, this is VDD, and just a very simplistic analysis, this is L, and say the linear distribution between source and drain, then it is simply can be written as VDD by L, right? So obviously, if you are reducing this L, then E is increasing, and we are assuming that we are not reducing this VDD right now. Okay, so you understood this electric field is increasing, right? So what is the impact of this high electric field in the mobility or carrier transport of a particular device? For example, if you consider the carrier electron drift velocity, say this is, if you plot the electron drift velocity versus electric field, it would look something like this, right? You know that. So electric field, this electric field, till when it reach, you start from here, go to EC, right? Till that, the drift velocity will increase linearly. Drift velocity increase linearly with a change in electric field, right? After that, if you whenever you cross this EC, the velocity, the drift velocity become constant at a value of Vsat. So further, if you increase it, it is not increasing, right? So here, so if you are reducing it, suppose if you are changing this, okay, suppose if you are operating in this region, if you are operating in this region, and when you are increasing VD, electric field increases, velocity increases, carrier is moving fast, right? But when you have crossed this EC, that phenomenon is not been observed, right? The velocity is become saturated. Now, tell me here, where is the mobility? Can you comment? Where is the mobility here?
Slope of the graph.
Slope of the graph. So, how mobility is changing with change in electric field?
A constant.
Yes, very good. So remember that. Okay, mobility does not change. Mobility is the constant as long as you are in the linear region, right? So as long as you are in the linear region, the slope is constant, and so does the mobility. So the mobility is slope equal to the mobility, right? So the mobility is constant in this region, right? Now once you have crossed this EC, there is no concept of mobility, Remember that there is no concept of mobility. Mobility just defines that if you what is the mobility just defines what? Mobility just defines what is the slope. Means if you increase electric field, what should be this d v drift, dip velocity. It is just that this part. It is nothing else. Okay. So once you have crossed this, it is no longer the concept of mobility is invalid. Now you have to simply say we have entered into the velocity saturation region, right? So that means velocity becomes saturated. So as the velocity becomes saturated, the dip velocity will become constant equal to v sat, and this effect will come into picture as you are reducing this gate length significantly, because then the electric field would be say somewhere here, right? And here you can see you are operating in the velocity saturation region. So earlier these equations, when they have derived, we have considered this dip velocity versus this electric field, and we are actually we have this region, means v versus e, where these equations are valid for this region, not for this. Right. So you can see this is type of a recap, but I thought this is important, so it is good to have a recap on that. So I have written all these things here, so anyway I will share with you, so I'm not repeating. Anyway, I have mentioned these things here, so you can read it from here, right? So now how can you get an idea or this current equations, an idea of how to get the current equation for a short channel MOSFET if we know the current equation for a long channel MOSFET? Say this is ID versus VDS characteristics. Okay, this ID VDS characteristics is something like this for a particular VGS, right? This is for long channel, right? Long channel MOSFET, right? ID VDS characteristics. Now here this is VD sat, right? Like this is the linear region, this is the saturation region, isn't it? Remember, this is ID. I am not plotting the velocity here, ID and VDS. Okay. Now yeah, what is happening here for short channel MOSFET, okay, that this VD sat, before you reach actually this VD sat, that is the this pinch off region, actually here actually the pinch off is happening, right, and the current is becoming saturated, right? So before the pinch off occurs, beforehand only, this current, you are reaching this region. Okay, see here you are increasing VDS. Please try to understand, you are increasing VDS, so current is increasing, right? But as this gate length has reduced significantly, so the electric field has increased. So suppose you are increasing and VSAT has increased, so no longer the concept of mobility has increased and it has entered into this region, this part, right, in the VSAT region. So when this VSAT it has reached to VSAT region, then what will happen? If you further increase also VDS, then you see this ID sat is not increasing. So the velocity of the carrier become constant, right? Velocity become become constant. That means the current will also become constant. So as soon as you hit this point here, you are going to see a saturation in current for this as well. Is this part clear to you? Is this part clear to you? Yes, Alicia?
Yes, sir, it's clear.
Okay, so if you have understood this one, then please tell me what would be the expected equations, okay, for this short channel MOSFET. Alicia, please tell me.
So it would be similar only. Only the VD sat would be replaced by a smaller value.
Okay, so please tell me. Okay, what would be the expression in the linear region? Will there be any change in the linear region?
No, sir.
No. Okay. But what about in the saturation region? That value will change, right?
Yes, sir.
Okay. So what is this? This VD sat, okay, for short channel. Okay. How can I represent it in terms of this transistor length, gate length, L, EC, and all this stuff? Can I write it like this? That VD sat for the short channel is equal to gate length into the critical electric field.
Yes, sir.
Can I write it?
Dimensionally, yes.
No, you think and then not only dimensionally, from other aspect as well. See here, this VDD, right? This VDD is equal to L into E, right? Am I not doing the same thing here? This is also VDD. VD sat means also VDD, isn't it?
Yes, yes,
So
sir.
this is
You
also
are right.
VDD L, and this value is EC, right? So this is also EC, right?
Yes, sir.
Right. Okay. Then probably this I can also write this V sat, right? The saturation velocity by mobility of this electron at this point, at this moment, right? Means here. Right. Anyway, this is just and how can I represent this EC in terms of VD sat and movement? This I can write. Okay. Now tell me what should be the equation?
ID is equals to again
ID
half
equal to
half mu and Cx W over L.
should it be half?
Um,
Are you getting in this saturation region?
no,
Think
we're
about
not.
it.
Okay, right, we're not.
You are not getting in the saturation region. We have not reached, right, saturation region. We are still in the linear region, right? For the if you consider from the long channel MOSFET, then we are still in the linear region only, right?
Yes.
Right. So let us start with that. So what is the expression for current for a long channel in the linear region?
Mu and Cx W over L, VGS minus VTH into VD sat SC.
Yeah, VDS minus VDS squared
S squared
by
divided
by
2.
2. Right? Okay.
Yes.
Now think about it. How should we change it here? Because see, till this equation is valid, isn't it?
Yes, sir.
Right. Now, can you comment then what would going to happen for this region? For this region.
Or even replace BDS with VD set.
Just replace VDS by VDS sat.
Very good. Very good. Just replace this VDS with VD sat short channel minus VD. This symbol I am using is pretty big, so VD sat then short channel is C. Okay, so the equation will become something like this, right? Isn't it?
Yes, sir.
Right. So again, then we have a relation for this current, gate voltage, drain voltage for long channel. Now also we have it for the short channel. So this expression is for the linear region and this is for the saturation region. Linear and the other one is for the saturation. Isn't it? But again, this is first order and empirical. Okay, so this is just for our hand calculations. Okay, but you know, we can, you know, with this simple approximation from the long channel MOSFET current equations only, we would be able to derive the basic equations for analyzing the short channel MOSFET. So please let me know if you have doubt in this part. Okay, then I'm assuming if you are not asking any question, then I'll assume that you don't have any question, any doubt. Fine. So then we can go ahead. Yeah, this is again one simple work for you. So now you have the equation for, where's my Gaussian? Yeah, you have both the equations in linear as well as in the saturation region. So now I can ask you anything. Anything means I can ask you to find the noise margin for short channel MOSFET. I can ask you to find the logic threshold for short channel MOSFET. Yes, that is exactly I am going to do now. So what
Sir,
about?
so what is the difference between the equations in long and short channel? I mean, we just changed the variable name, right? Actually, the saturation voltage values are different, but rest things are same.
Right. Rest of the things are it ours means you are right.
Sir,
Rest of the
only the
things are
saturation voltage has changed. So what's the difference between short and long channel MOSFET?
short and long channel MOSFET. Here we are not even going. Here the current saturation. This current saturation is due to pinch off. Right. Here the current is saturating because of velocity saturation. This is one of the major difference.
Sir, like I mean to say, what matters to us are the characteristics, right? What what triggers those characteristics is not required in the final circuitry, right?
Right.
If it gives the same characteristics, then it's same for us.
And see that's what again I'm trying to explain to you. See, okay, if you put it in this way, see, in saturation, okay, in saturation, what is the relation between ID and VG for short channel MOSFET? Ash?
The square relation.
No, please check it. It is not square here.
So,
Right? Arsh, what happened?
yes, sir. Okay. So the second equation is for the saturation region of the short channel MOSFET.
Yes.
Okay, I get it.
You understood, right? So you can see here, this ID is
Yes,
now
sir.
proportional to VGS, right? In previous
Yes,
case,
sir. Yes, sir. I
you understood, right? Yeah. In the previous case, Ig was proportional to, in saturation, proportional to VGS square, right? So that's how you are, that's what, we have spent some time in saying, right? That the characteristics, output characteristics for long channel MOSFET would look something like this, where you can see the in separation between this consecutive VGS line would keep on increase as you are increasing VGS, whereas for short channel MOSFET is expected to be in the equal, right? That is what we have discussed beforehand. Na? So you can see the same phenomenon you can also observe from this equation, which we have derived from the long channel MOSFET only by doing some manipulation. Right? Okay. Then, so if you have no more question on this short channel MOSFET equations, and you know both the equations in both regions, linear and saturation, then next question is, please find the logic threshold for short channel MOSFET. Sorry. So how you are going to do? Anyone? Maybe Shubhayan? Shubhayan? Okay. What about Ranbir?
So we will put
Okay, yeah, Shubhayan. Yeah.
V in equal to V out, something like that.
Yeah, means the same thing, right? Equate
Yes,
the
yes.
both, equate the saturation current for both PMOS and NMOS, right?
Yes.
Right. Equate IDA sat for both PMOS and NMOS and find the V in, right? That is basically would give you the logic threshold for this MOSFET. So I am not doing it. This part, if you want to see, it is given in the book Rabe. You can consider this Rabe's book. The procedure, the process is already been given. So again, this is just simply, again and again we are doing type of repetitive things. So it is basically just equating the NMOS and PMOS and just do some manipulation. That's all, right? Nothing new theory here. So I am just skipping this one. Right. Now, before I go into this, can I take a 1 minute break? Okay, so I'm not stopping the recording. Okay, it will continue, but just want to take 1 minute break. Just come back. Huh? Yes. So, yeah. So I hope you are also back. So two important aspects regarding this digital IC design. One important thing is power, and the other one is delay. Right?
Sir, one question. The VD set for PMOS and NMOS are different, right?
VD SAT for PMOS.
And
For
NMOS.
PMOS and NMOS are different. Yes. So we can keep it like this. So for PMOS, we can write it at like VD SAT N for NMOS. And for PMOS, we can put VD SAT P.
Okay.
Okay. Yeah, they are different because one is for whole and the other is one for electron. True. Right. So one is power, the other one is delay. Right. Now, 1 minute. Let me see the next one flow so that fine. Okay. So okay, power, right? So we have already discussed about the static power dissipation. Static power dissipation. And in CMOS, ideally, we can expect there should not be any static power dissipation, but unfortunately, this is not true because of this subthreshold leakage. There will be some static power definition as well, right? And static power dissipation will always be there as long as the transistor is on, means, and they are in the and the input is static. That means either 0 or 1 at logic 1, right? As long as the input is at 0 or 1, there will be always an static power dissipation, right? Because of this leakage, right? Okay. Okay. These discussions like power and delay, right? They are not actually completely like related, means not only related to the CMOS inverter, but you can relate these things with the other inverters like other NMOS inverter, which you have discussed, NMOS inverter with resistive load, NMOS inverter with enhancement load, with them as well. So you can say this is type of a common discussion, right? So one is the static power like static power dissipation, and the other one is the dynamic power dissipation. Right? Dynamic power dissipation is means like when you are switching, right? This is when you are switching, right? Then you are charging and discharging the capacitor, right? So you have this inverter. You are charging then discharging this capacitor, so that also consumes energy, so you're losing some energy in that process as well, right? Now there are other
So this dynamic power dissipation is basically for the amplifier region, right?
is basically in the yeah, there is actually we will take one separate separate class only on the power dissipation, where we will discuss more on this. But what you were trying to say, I think you were trying to say when there is a direct path between this VDD and ground, when both transistors are in saturation, right? So that is actually referred as direct path power dissipation, and when both transistors are switched on. Okay, so that is called direct path power dissipation when both transistors are on. So dynamic is primarily the charging and discharging of this capacitor, because when you are charging this capacitor, some power is also been consumed, right?
Yes.
Right. So, and this dynamic power dissipation is proportional to the frequency, the clock frequency. The clock frequency means basically how the input is switching, or how frequent the input is switching. The more the number of switching, the more will be the this dynamic power dissipation, right? Okay. Again, this static power dissipation and dynamic power dissipation, they are also related with the temperature of operations and all this other stuff as well. So this is quite we are doing some simplistic analysis as of now. And the other thing is the delay. I think for delay I have just a minute. Let me see that whatever power dissipation in IC. Yeah. So yeah, regarding delay, I think 1 minute. Let me just check it. I think delay I have discussed it more on this. Now propagation delay. How is it measured? Estimate the delay. Yeah, I think here. Yeah, fine. Yeah. So delay you have understood that if I give some input here, right? When you are getting the output at this output side, there will be some in terms of time gap or time space, you will have some gap, right, between whatever. Suppose if this is the input and this is the output, right? Then you will have, suppose from here till here, you see there is a gap in time. This is the time axis. There is a delay between input and output, and that basically caused due to this RC delay, that resistance offered by these transistors and the load. That is basically load capacitor, right? So with this for this delay we will take, and today only we are going to discuss it a little bit more on this, right? But this is just a small introduction on this, that now we are now onwards we are going to focus primarily on these two things, one power, and the second thing is on the delay. Right. Now regarding power, let us consider a simple inverter where this is the inverter PMOS NMOS, output CL, and this is the load CL, and this is the input, which you can see that input is changing from 0 to 1, right? Input is switching from 1 to 0, right here, right? Now here we need to estimate what is the total dissipated energy, right? So could you quickly calculate? Because these are the things, I believe that you would be able to do it. What would be the dissipated energy? Yes, Arsh?
So half CL VDD square.
Okay, why you are saying it should be half?
So like because the energy stored in capacitor would be that at that time, and when V out goes to zero or from
I
zero to
think I
one,
have
that much
not.
energy will be
Yeah,
stored.
you were right, Arsh. But I have asked something else. I have not asked what is the energy stored in this capacitor. I have asked what is the energy dissipated. Okay, while this capacitor, see, this is going from 1 to 0, right? So that means this is going from 0 to 1. So the capacitor has to charge from 0 to VDD, right? So during this process, what is the energy dissipated? Okay, the total energy taken from this VDD source. Yes, Harsh. Then please comment on
Sir,
your previous answer.
I'm thinking, sir.
Okay, what will be the energy consumed from this source? From this here also, right? You have something, right? Will there be any energy consumption from this source which is
No, sir.
connected? No, no, right? It expected to be no because
No current.
no current, right? IG is ideally again
Exactly.
that is not correct. Means completely right. Not,
There
but
will be
that is not
parasitic
true.
capacitances, so there may be
Yeah,
some.
right, true. So we are assuming no no power consumption from this side. So we are considering whatever energy is coming from this VDD, and that is being dissipated here. So basically now you are considering a path which is this. So during this charging process. Yes, Ranbir, can you comment?
Sir, VDD into like we can calculate ID.
VDD into ID, but don't we do have to means see okay, when this has started charging, will it charge immediately capacitor?
No, sir. No, sir.
No, right? So it will also take a right, it is open, then the current will also change, the voltage will also change. So can we take direct multiplication or do we have to do an integration?
We have to do an integration.
Right, right. Then can I simply write it like this? Can I write it like this?
Yes, sir. ID of this.
It should be VDD.
Which one? Should be VDD?
So instead of V out, we should write VDD.
Okay. No, V out, I'm saying this one.
So the upper limit should be VDD, I guess.
This upper limit here we are doing in
Oh,
terms of
sorry
time.
for time, right? Yeah, sorry.
So finally we can put it in VDD, right? Okay, so if you have that one, look, let me just put it V. Okay, say it is V. Yeah. Then what is the current flowing through a capacitor? What is V out? Maximum voltage. This maximum voltage going to be this V only. Uh-huh.
So it can be written as C into D V out square by 2.
Are you saying it correctly? C into, please say it again. C into
So D of V out square by 2.
by 2. Will it be by 2? That's what I wanted to know. Will it be by 2?
Yes,
Sir, if we calculate this thing, it will be the energy stored in the
yes.
capacitor, not the
Right. If we store, okay. Again, we are going to calculate that as well. We are going to do two separate calculations. One is the what is the energy stored in this capacitor, and the other one is the what is the energy dissipated from this source. So, okay, how can I find energy dissipated from this voltage source? Please tell me that.
V into Q, that is CV square.
I think I was doing it correctly earlier.
Sir, sir, can you please explain why did you put VDD constant? I mean, the energy dissipated would be the voltage into current integration, right? So the voltage across the capacitor is varying. Why did we use VDD directly?
So
Yes,
because we are calculating the
because
voltage loss at the source, power loss at the
at
source. So
right, right, right,
calculate the
exactly.
source voltage and the current from the source.
Right, exactly, exactly. That's what I asked you, na, Arsh, that like we will calculate both. We will calculate what is the energy stored at this capacitor. When we are calculating what is the energy stored in this capacitor, then the voltage the voltage change across the capacitor we should also consider, right? But here, what we are considering, what is the energy that is taken from this volts, VDDs, right? So there, the VDD is constant.
So,
So
sir,
that
the extra energy then is lost in the PMOS while the current
uh,
flows.
exactly, exactly, exactly. That's what I wanted
Okay,
to
sir.
show you from here. Exactly. That is what I wanted to show you from here. So you have understood, right? So this is the energy, this energy that has been taken, okay, from this VDD during this charging process, right? Now we will find what is the energy stored in the capacitor during this process. Energy stored in the capacitor. So that is, say, like EC we will write. Again, that we can do integration 0 to infinity IC of t. Then here it is V out of t, here dt, right? So here, if you put, it would become 0 20, this one C dV out by dt, and here it is V out dt. So if you calculate, it would become half, then C square. Right. Is this fine to you? Yeah, Shamak and Arsh. Is this fine?
Yes, sir.
Okay. Right. So you can see here, this is the total energy taken from this source, and this is the amount of energy energy stored in this capacitor, right? After this capacitor has completely charged, right? Then, and but you can also see here half of the energy, then this energy, the stored energy, is actually the half of the energy taken from this source. Then where is the rest half of the energy? So rest half of the energy, that means half of C VDD square, right? Half of C VDD square, that has been lost at when it was charging through this PMOS. So is this part clear to you? During charging, when it is charging, half C VDD square, this amount of energy has been lost across, means lost means across like I said, heat dissipation across this PMOS, right? Now this is the charging one cycle. Now when it will discharge, what will happen? This half C VDD square, that amount of energy will also get dissipated, but this time it will be dissipated across this NMOS, right? So you can clearly see half of the energy is lost here, half of the energy is lost here. Any question, comments on that? This is one of the important thing that we should understand and we should make ourselves aware of. No, right? Okay. Then, you know, so that we do not forget, let us also write it. Okay, this thing here. So, half of the energy delivered by the source, that is VDD, is stored in the capacitor. The remaining half energy is dissipated as heat in the resistor during the transition. Resistor means the equivalent resistance of this transistor, right? Then during discharge phase, that is V to 0, the energy stored in C gets dissipated in the resistor. So here this resistor means here it is basically NMOS, and here this resistor means it is basically the PMOS equivalent resistance, right? So I hope this part is clear to you. This is an very quite important thing that we should understand and we should know. Fine. Okay. If there is no question, then we can move forward. So, like, while considering the power dissipation, so there are a couple of terms which are important, and we should know in what context they are important. Right? So here, as you can see, a brief note on this power dissipation in IC. So depending on the design problem at hand, different dissipation measures are considered. For example, so suppose if you have given a peak power, okay, limitation on the peak power cannot be more than this, right? So, what are the things that you should, keep in your mind? Like, peak power has been given this one. So these are the things I should keep in mind. So for example, when the peak power is given, so important is that when you are studying the, supply line, or you are making the, what should be the line width. For example, you have made one line, okay, say this power line, right? So power line, so it has a particular thickness. So if you consider it to be like three-dimensional view, right? So, and the current is flowing like this, right? So this wire or this line cannot handle more than this amount of current, right? So that way, that peak power in your particular circuit is this much. So while you are doing that, because see, voltage are not changing, right? Voltage you have kept it fixed, right? So because VDD is fixed. The only thing is that all of a sudden the current can change. So the wire that you are providing, or the metal lines that you are providing, or maybe the polysilicon lines that you are providing, that should be able to handle that current, right? So that way the peak power, when you're considering the peak power, that would be important when you are sizing the supply line, right? That is important. So peak power is basically, this I peak into this V supply voltage, or basically the VDD, right? So it is basically the maximum of this PT, and you understand like maximum of PT when it is important, when you are considering, right? You have to keep a provision for this much power, so that your IC should be able to handle this much power, right? Then another term is the average power. So when you should consider the average power is important when you're considering the battery requirement. You will not when I say like the average power consumption of this is say this much milliwatt. So that doesn't, that means, you understand, right? I have a this milliampere hour battery. So how long my battery lasts, right? If I use this one. So while considering the battery requirement, right, then this average power is important. And the one of the another important thing is that the cooling requirement, right? If you say like the IC here, the average power is say 0.5 watt. So then, 0.5 watt, that means half a watt. So I should maybe provide one small heat sink for that particular IC, okay, so that the heat would be able to dissipate. So right, so from this average power I will get those type of idea, right? What should be the battery requirement if it is an type of battery driven device, or what is the cooling requirement for that particular device. And this any average, P average is basically over a time, over a particular time frame. So 1 by T, it is basically the time average of that power requirement, right? So basically V supply is not changing. So V supply, so basically it is the average of this V supply in average of this time, average of this current, right? These are small like points that also you should keep in your mind. Right. More discussion on this power related thing and on CMOS inverter itself, we will take maybe in a later stages. Then another important, as I mentioned earlier, the propagation delay. Right. So what do you mean by propagation delay, and how to measure it? Right. So what is propagation delay? Propagation delay of a gate is basically that how quickly the gate responds to a change of its input. So suppose this is an gate, okay. Say this is an OR gate, right? Digital gate. So you given if I change this input, right? For this OR gate, suppose this is a 2-input OR gate. So one of the input you have changed, other one you have remained fixed. Then how quickly that change in input will be reflected in the output, right? So that basically gives a sense of like what is the propagation delay, right? Or in other words, it is expressed by the delay experienced by the signal when passing through the gate. So that means as if when it is passing through the gate. So suppose after this OR also, say this is say like 0. Okay, this is 0. So here earlier the output was 0 only, right? 0, 0. So output is 0. So now it is like 0 to 1. So output is expected to be 1. So the output has also changed, right? So this is the change in input and this is the change in output. So there is definitely some delay between them, right? So while passing this input from this side to this side, you can think that way. So what is the delay experienced by that input signal when passing through the gate, right? Now the important question is that how to measure this, propagation delay. That is very important. Now in this context, what we do, we take the we will take an 50% transition points, okay. So this delay is measured between the 50% transition points of the input and output waveforms. So what do I mean by that? Or maybe before that I can write it. So it is measured, I am writing so that from this it would be easier for you to later on study. Measured between 50%, okay, between the 50% transition points of inputs and output. So what do I mean by that? Suppose if you have an input like this, like as you can see from here, okay, and your output is say like this. So 50% of the input means this is say V, this is 0, this is again 0, this is V. 50% means here, because it is type of step input. So 50% here, and here 50% is this much. So For here, we will define the delay is the time gap between these two.
So why are we assuming that the input is ideal?
Very good question. 50% of V. I wanted to write here half of V, but every time I'm writing here. Yeah. Right. Why you are considering the input to be then step input, right? Okay. Let us not consider the step input. Fine. So let us consider the input is like this. Okay. So here the delay would be between this. Okay. So it does not matter whether the input is a step input or this one. So the definition of delay is always the same, right? Is the 50%, and here also the 50%. Now the question is why we are taking 50%? What is this like? Why you are taking 50%? Means any idea like any thought? What could be the reason?
Maybe
The
because
average of the
switching,
Mm-hmm.
like the switching threshold is also taken at half. So
Exactly. Yeah, this is actually primarily inspired from that point only that we have considered that VT is also the half of VDD. So if this is VDD, then the threshold is half of VDD, right? So that is basically the changeover point, means crossover point from one state to the other state. Right? So maybe that. This 50% that also I want to write it here. Definition is inspired by the assumption that the VT, you remember VT is the switching threshold. VT is typically located in the middle of the logic swing. Logic swing is 0 to VDD, right? So this is one thing to important, like you should understand like why we are interested in taking it to be nearly from 50% to 50%, right? Okay. So yeah, and regarding in the context of this digital IC, we would like to also have it like this. Suppose in case of this CMOS inverter, right, it is like this, right? So when you are considering that charging of this output capacitor, load capacitor, right, say this output will charge, so it is from like 0 to this VDD, it is changing, this is VDD, and while it is changing it should charge through this PMOS only, then this is off, and in that stage the input is like this, right? Okay, so while it is charging, right, while it is charging, um, then you can see here one thing that it is charging through this PMOS, right? So this PMOS as an, you can consider it, if this PMOS as an equivalent resistor, then it's basically one resistance and it is charging this capacitor CL, right? So that way, and it is VDD, right? So that way, this is basically nothing but and simple RC circuit. So we can use, the often use the first order RC model, okay, to represent the or to estimate the delay, okay, for these digital ICs, and that is also we are going to do here. So we are trying to estimate the delay from the first order RC network, and I hope you have realized why I have drawn this type of circuit, because you can make a correlation between these two. This circuit, this is turned on immediately when this is you have applied 0 voltage here. So that way you can say like this voltage is this type, right? Sharp. And to make our calculation bit easier, we are considering that here the input is some step input, right? So here the input is step input. So that means this is one step input, and where for this step input, we are going to see that what is the change in this output, right? Right. So this is well known RC, very simple network, and you know the output voltage, how the output voltage will vary over time, right? So this output voltage, so as soon as it is on, so capacitor will start charging, and the voltage across the capacitor will start building, right? And it will take somewhat this type of shape, right? Where this is actually, if you say like this is VDD, then VDD, it will be almost constant to VDD after that with respect to time, right? Okay. Now, if you have to consider the delay, okay, on the time scale, okay, on the same time scale, 0, and this is V input. Let us also, just for our understanding, let us also plot this input. This is input, right? So if you now want to estimate the delay, so delay is basically, we have to then find where this output voltage has reached this VDD by 2, right? Then basically this much is the propagation delay, TP, right? Now, can you tell me what would be the propagation delay for this simple circuit? Yeah, anyone, maybe who want to tell? Arsh, Alisha, Shommuk, Shubhayan, Ranveer.
So can you please repeat the question?
Yeah, what the delay? TP here.
Sir, RCL LN2.
R
RCL
CL into.
LN2.
Okay, how do you find? Okay, maybe I know. Let us do it step by step. Okay, how can I write V out? V out in terms of this R and CL.
So V in into 1 minus e to the
What
power
would be the
minus t by
expression?
R's.
VDD into 1 minus e to the power minus t by
Minus T by
RCL
right, right.
into VDD.
So please check. Can I write it like this?
Yes.
Into V. I can write this, right? So we are trying to find that when V out of T, you will be equal to VDD by 2, right? So we will put that. So here it is basically VDD by 2, right? And it is 1 minus that T by REL, and here it is T, right? So just do a little bit simplification, and we have to find what is the value of T from here, right? So if you calculate, it would come something like this, that it would be ln of 2 RCL, right? Then ln of 2 is basically 0.69 RCL, right? So here TP is equal to 0.69 RCL. So this 0.69 term, this is important, and you will see that this will be coming again and again in our writing, in our write-up. So this TP would be 0.69 of RCL, and that's how it comes. Quite simple, right? Now, that is fine. One more important thing is also there. Probably that I should discuss it right now only. Can you tell me if I want to find the time when the output reaches to 9% of VDD? So what would be that time? Let me very quickly. We don't have much time now. To reach 90% of VDD. Just simple calculation. Tell me, do it and tell me. Yes. Shubhayan, can you tell me?
RC LN10.
2.3 RCL.
Around 2.3, huh?
Yes.
Yeah, 2.3 RCL, right? Okay. Sometimes this RCL is also written as tau. Okay, the basic time constant. So that way it is written as this 2.3 times of this tau. Anyway, that those part we can discuss later, next class. Okay, let me see that what is the next thing that I can. Yeah, probably this one I have 2 minutes. I can finish it. This is some very simple thing. Okay, so then in the context of this inverter, right? So here you can see this is an CMOS inverter. So you have the input like this 0 to 1 transition step in. You can have a transition 1 to. So okay, okay. For the second case 0 to 1, your output would be like this. So capacitor would be charging, right? So as you can see for this case, capacitor would be charging. So here this would be the delay, right? So this is one delay. Similarly, if you consider the other one, the green one, for this input, the output would be, I think I should have used here this color, and I should have used this color here, right? And for this input, the output would be like this. So here you have one more delay, right? So this particular delay, okay, when the output is changing from high, propagation delay HL, TP HL, TP high to low, and this is called TP low to high, TP low to high. So TP high to low, TP low to high, right? And the propagation delay on and the average and the propagation delay for CMOS inverter is defined as half of TPHL plus TPLH. So this is important. I'm doing hurry because that's not much. So right. So this is important. Propagation delay in case of a CMOS inverter is the half of TPHL. Basically, what we are doing, we are averaging. We are doing the average out of these two. Right. Okay. So here just one small thing. So you can see for this inverter, we have given one input. So this one, this orange color is the input one, and this, as a result, the what we are getting is the blue color, which is at this output. So you can see here, when this is 0, this is 1. When this is 1, this output is 0, right? And when it is doing the transition, output takes some time to follow the input, change in the input, right? Okay. So clearly, if you have to define, then what is the propagation delay? Now we have seen there are two types of propagation delay, TPHL, TP. So can you tell me what would be quickly? This TP, TPHL, right? Okay. And what would be this? TPLH, right? Okay. And there just one more minute, just not even one more minute I need, even lower less than that. So you can see this output, or here you can see this output is taking a time of this much to change from 10% to 10% to 90%, right? So this is called rise time. So this is called rise, 10% to 90%. This is called, and this output is taking this much time to fall from 90% to 10%. This is called fall time, TF. Okay, so this is just simple notations that we will be using throughout our further analysis. This is rise time, and this is fall time. Okay, I think with this we should stop here. So yeah, thank you. and we'll start from again a little bit recap with this in the next class. So I request you to, I have given you one homework, right? That is this one CMOS based on the CMOS inverter, right? CMOS inverter, you have to find the noise margin. Yeah, this one. So please try to find this one. The solution I will provide tomorrow. Okay. And also, today only, make some time and please recap these couple of things. Okay, these are very important and quite fundamental for rest of our discussions. Okay, then. Thank you once again. So I'll see you next week. Next class.